Hello everyone, welcome to Mida Physiology Blogs. I am Dr. Sonam. Today we are going to discuss about the reabsorption process which occurs in the renal tubule. The objectives of today's video are to know about the tubular reabsorption and also to discuss about the glucose reabsorption in the renal tubule. So let us see what happens in a nephron. We all know that the blood which is coming in the afferent arteriole is now going into the capillaries, and from these capillaries via the glomerular membrane the blood would be ultrafiltrated, and this ultrafiltrate which is formed is now running in the renal tubule. So the first step which occurs in the nephron is filtration, and then there will be the formation of ultrafiltrate. Now this ultrafiltrate, when it is running in the renal tubule, it undergoes two processes. The first one is the reabsorption, so that the water and electrolyte present in the ultrafiltrate would again be reabsorbed back into the circulation. And the second one is the secretion, so that the unwanted product of the blood in the peritubular capillary could again be secreted into the lumen of the renal tubule, and ultimately the urine would be formed and then it would be excreted out of the kidney. So here, this second process, the reabsorption process, is very important, because when the blood is being filtrated out of the capillary into this space, into the Bowman's space and into the lumen of this renal tubule, remember that initially the osmolality of this ultrafiltrate is equivalent to that of plasma, because the water and electrolyte composition of this ultrafiltrate would be similar to that of plasma. So you see, if all this water and electrolytes which was similar to that of plasma is eventually coming out of the urine without the role of reabsorption, then the water and the electrolyte depletion would lead to various disorder in the body. So the reabsorption of those water and electrolyte back to our circulation is very important. And similarly, when we say that the filtration is occurring from the capillaries and this filtration rate is 125 ml per minute, or in a day it is 180 liter per day, okay, what we are going to say is 180 liter of blood is being filtrated in a day. But we do not have 180 liter of blood in our body. So how is that possible? Because of this reabsorption process only. The blood which was filtrated is again being reabsorbed and going back to our circulation, and again it is coming towards the nephron, again being filtrated and being reabsorbed. Okay, so this reabsorption process is very important. Now let us see how the reabsorption occurs in the renal tubule. The ultrafiltrate which is coming in the lumen of the renal tubule, for the reabsorption to occur, they can undergo two pathways: the transcellular pathway and the paracellular pathway. In the transcellular pathway, these electrolytes, they would firstly bind to the receptor which is present in this apical margin or the apical border or the luminal border, and those electrolytes would be now transported inside the cytoplasm of the epithelium, and from the cytoplasm it would be again transported into the interstitium with the help of another transporter which is present in the basolateral side. So this process which is occurring through the cell only, okay, this process is the transcellular pathway. And since maximum of the reabsorption occurs in the proximal convoluted tubule, because we know the ultrafiltrate is firstly going to encounter the proximal convoluted tubule, then the transporter present in the proximal convoluted tubule is responsible for the maximum reabsorption of water and electrolyte as well. Now in the PCT, the epithelia are arranged in such a way that in the apical portion they are connected with each other with the help of tight junction, and in the basal side they use the space which we call lateral intercellular space. Now what may also happen is the water which is present in the ultrafiltrate may even cross through this tight junction, reach to the lateral intercellular spaces, and along with that water the minute amount of electrolyte dissolved on it would also now be reaching into this lateral intercellular spaces and into the interstitial side. So these transportation which is occurring in between this epithelia, in between this cell. This process, you call it, the transportation is via the paracellular pathway. So the paracellular pathway or the transcellular pathway, both are now going to reabsorb the substances, and then it is giving the substances in this interstitial fluid. Now from this interstitial fluid, the substances has to move into the blood in the peritubular capillary. We know that the blood in the peritubular capillary has the lower hydrostatic pressure and the higher osmotic pressure. So there will be the ultrafiltration, or the bulk flow will occur along the osmotic gradient. And then the reabsorption of the substances would occur back to the peritubular capillary and into our circulatory system. So you see, when this transcellular pathway is occurring, the transportation reabsorption process is occurring, the most of the substances present in the ultrafiltrate, they are water soluble only. Now these water soluble substances, they cannot easily pass through this apical lining, apical margin. They cannot easily pass, and they cannot easily go into the cytoplasm, okay? Because here you see this apical margin, like any other cell membrane, is made up of this double lipid bilayer, and if the substance is water soluble, they cannot cross through this lipid bilayer. Then obviously they have to take help of this protein, okay? This protein, if they are the channel, the transportation of the substance would occur via the simple diffusion. If this protein is the carrier, the transportation is occurring via the facilitated diffusion process. And if this protein is the pump, there will be direct utilization of energy, and the transportation, you call it primary active transport, or sometimes there can be the secondary active transport with the help of symporter or antiporters. Like you can see here, this is the luminal side, and in this luminal side, the sodium and chloride is trying to be reabsorbed, okay? So in this epithelium, you see there is the protein molecule. This protein molecule is now together, is acting as a transporter, and it is together transporting the sodium and chloride inside the cytoplasm of the epithelium. So this is a symporter, and it is undergoing the process of co-transportation, secondary active transport. Similarly, in another example here, you can see here with the help of this protein, only sodium is being passively diffused inside the cytoplasm. So it is a channel, okay? So there are various kind of transporter present in the apical site, due to which the substances would now be reabsorbed into the cytoplasm of the epithelium. Now from the cytoplasm, it has to be transported into the interstitium, for which again there are another set of transporter in the basolateral side. Okay, the most common transporter over here you can see is the sodium potassium pump. Similarly, you can also see here in this picture the potassium chloride co-transporter. There is the chloride channel also, okay? So you see the set of transporter present in the apical side or in the basal side is basically helping in the transportation reabsorption of the substances along the transcellular pathway. Now let us see how much amount of substances are being reabsorbed, how much percentage of the substances are being reabsorbed from the ultrafiltrate. When you talk about sodium, normally 98% of the sodium present in the ultrafiltrate, it is being reabsorbed. 94% of the potassium is being reabsorbed, which is present in the ultrafiltrate. And in case of glucose and bicarbonate, normally 100%, all of them, they are reabsorbed, due to which in the urine, the amount of glucose and the bicarbonate would be nil. Similarly, the reabsorption of the chloride, calcium is also higher, but the urea, it is lower. You can see the urea reabsorption is only 53%, and maximum it is excreted, that is 47% it is excreted in the urine. In case of water, it is reabsorbed 88 to 90%, and only 10 to 12% of the water in the ultrafiltrate is being excreted. So today we are going to talk about the glucose transport. Remember, the transportation of the glucose through the renal tubule is always reabsorption. Okay, so this reabsorption of the glucose along the renal tubule occurs with the help of this co-transporter, which we call sodium glucose co-transporter. Okay, so this is SGLT, that means S for sodium, then GL for glucose, and T for transporter. Okay, so this transporter is present in the apical or the tubular side, and since maximum reabsorption occurs in the PCT only, this sodium glucose transporter is also working maximum in the proximal convoluted tubule luminal side only. For this co-transporter to occur, the glucose would be reabsorbed only when the sodium is also being attached with this transporter. Okay, and both of the sodium and glucose is now being transported along the same direction. Here the glucose is being reabsorbed and the sodium is also being reabsorbed along the electrical and along the concentration gradient. Okay, and this electrical and concentration gradient is being maintained by the sodium potassium pump, which is present in the basolateral side. Because of the sodium potassium pump, there will be more efflux of the sodium outside into the interstitium, due to which lesser amount of cation is leading to electronegativity and lesser amount of this sodium is leading to decreased sodium concentration, and both of them is favoring for the reabsorption of the sodium into the cytoplasm. And during this process, the glucose would also combine to that same transporter and the glucose will also be reabsorbed. So you see, the functioning of this sodium glucose co-transporter is depending upon this sodium potassium pump, which is directly utilizing the energy. Okay, so this sodium glucose co-transporter, which is an example of the secondary active transport, we say they are indirectly utilizing energy because the energy is not utilized over here, but for its functioning, the sodium has to be moved inside the cell, right? And that sodium to be moved inside the cell happens only when the sodium potassium pump is working. So the utilization of ATP is in this region, due to which the sodium glucose co-transporter is functioning. So it is like an indirect utilization of ATP. And via this sodium glucose co-transporter, the glucose which has been transported inside the cytoplasm, now this glucose is now being transported into the interstitium with the help of the carrier. Okay, the name of this carrier is GLUT, that is glucose transporter. So this glucose transporter type 2, so this is GLUT2 transporter is present over here, which via facilitated diffusion is now causing the movement of glucose into the interstitium. And now this glucose and the sodium, okay, which is present in the interstitium, would be now moving into the peritubular capillary via the bulk flow. So you can see here again the sodium glucose co-transporter, the SGLT can be type 1 or type 2. The type 2 is mostly found in the kidney, and in this type 2 sodium is binding with this co-transporter and one glucose is binding, and then only the movement of the substances can occur in the same direction. Okay, so this is a sodium glucose co-transporter type 2, and then for this functioning, the sodium potassium pump is playing important role, and the glucose which is being reabsorbed is now going into the peritubular capillary with the help of this GLUT2 carrier. So you see, whenever the plasma glucose level is increased, the rate of filtration of glucose will also be increased, and the reabsorption of the glucose will also be increased. But this reabsorption of the glucose, when you are saying that the glucose reabsorption is 100%, this 100% of the glucose reabsorption also occurs only up to a certain limit, because after the plasma glucose level of the glucose reaches a certain limit, then the glucose will start to appear in the urine. Okay, and this point, when the glucose will start to appear in the urine or the glycosuria starts, that plasma glucose level we are calling the renal threshold for glucose. Okay, so this renal threshold for glucose, they are found to be 100 milligram per deciliter. When the plasma glucose level is more than 180 milligram per deciliter in the venous blood or 200 milligram per deciliter in the arterial blood, then the glucose will start to appear in the urine, and this thing we call it the renal threshold for glucose. Now let us calculate the filtration rate of glucose. Whenever we are trying to calculate the filtration rate of the glucose, firstly we have to know how much is the concentration of the glucose in the plasma only, and then since the filtration is occurring via the glomerulus, we have to know what is the glomerular filtration rate. Okay, so taking in account a plasma glucose level of 80 milligram per deciliter and GFR of 125 ml per minute, you can calculate the filtration rate of glucose is plasma concentration of glucose multiplied by GFR, that is 80 into 125 would come to be around 100 milligram per minute. Okay, so when the plasma glucose level is 80 milligram per deciliter and the GFR is 125 ml per minute, at that time 100 milligram of glucose is being filtered in a minute. Now when this amount of filtration is occurring of the glucose, okay, this amount of glucose is being filtrated in a minute, then at that time the reabsorption rate is 100%, because at this time the plasma glucose level is below the renal threshold, so the renal reabsorption should be 100%. That means the renal reabsorption rate would also be equivalent to the filtration rate of the glucose. So here at plasma glucose of 80 milligram per deciliter, now we can say the reabsorption rate can also be 100 milligram per minute, as the reabsorption rate is 100%. Now what they have found is the maximum amount of glucose which the renal tubule can reabsorb is around 375 milligram per minute in case of male and 350 milligram per minute in case of female. Okay, so this is the transport or the reabsorption maximum for the renal tubule for glucose. Now we have just calculated that when the reabsorption rate of glucose was 100 milligram per minute, the plasma glucose level was 80 milligram per deciliter. Now at this level, when the reabsorption rate is maximum 375 milligram per minute, now we can calculate how much can be the plasma glucose level. Okay, so by this simple mathematical calculation, we will come to know that at the maximum reabsorption rate of glucose, that is 375 milligram per minute, the plasma glucose level would be 300 milligram per deciliter. Okay, so that means when the plasma glucose level is 300 milligram per deciliter, the renal tubule would reach to the maximum limit of reabsorption. That means after the plasma glucose level is 300 milligram per deciliter, the glucose will start to appear in the urine. Okay, so you can say that now this plasma glucose of 300 milligram per deciliter is also a renal threshold for glucose, but this is via the calculation only. Okay, so this renal threshold for glucose, which is calculated one, is different from the actual renal threshold for glucose, which is 180 milligram per deciliter in case of venous blood, or more than 200 milligram per deciliter in case of arterial blood. Okay, so there is the difference in the calculated or the theoretical renal threshold for glucose and the actual renal threshold for glucose, or the point at which the glucose will start to appear in the urine. And due to this difference, when we are plotting this all mechanism in this graph, there you can see slight deviation. This deviation is what we call splay. Okay, so here you can see the horizontal line is the plasma glucose concentration in plasma, and the vertical line is the glucose rate. Okay, and in this graph we have three curves. This is the curve associated with the filtration. This is the curve associated with the reabsorption rate. This is the curve which is associated with the excretory rate. Okay, the urine, the glucose excretion in the urine. So you see, whenever the plasma glucose concentration was increasing, okay, from 2, 4, 200, 300, 400 milligram per deciliter, similarly, the filtration of the glucose would also be increased, because the GFR over here we have taken is 120 ml per minute. The GFR cannot be increased, but for the filtration rate to calculate, we have to calculate the plasma concentration of glucose times the GFR. So along with the concentration of the glucose increase in the plasma, the filtration rate would also be increased linearly. So this linear line is the graph of the filtration rate. Now when you're talking about the reabsorption, you see initially when the plasma glucose concentration was increasing, the rate of reabsorption was also linearly increasing, right? And then it will reach to a maximum value. Okay, this maximum value we have found it to be 375 milligram per minute. So at this point you can see it is 375 milligram per minute. Okay, and this 375 milligram per minute, after that there will be no more reabsorption curve going upward, but now it is in the plateau phase, because this is the maximum reabsorption which the renal tubule can do, okay, for the glucose. So you see, if the renal tubular maximum reabsorption for the glucose is 375 milligram per minute, below that theoretically all the glucose should be reabsorbed, due to which this line, the reabsorption line, should be in a linear relation, okay. But what we have found is the reabsorption curve, instead of being this sharp and angulated, okay, the reabsorption curve is slightly curved like this. The actual reabsorption curve is slightly curving like this. We can see this curving, okay, instead of this angulated portion which is formed by this dot line. Now we know that the renal threshold level for the glucose actually is around 200 milligram per deciliter. Here you see, when the glucose concentration in the plasma is 200 milligram per deciliter, at that time you see the excretory rate has now slowly increased, right? So after 200 milligram per deciliter only, what you see, the excretion has started. And in this point, when you see in the reabsorption curve, instead of being sharp and angulated or having linear relation with the plasma glucose level, this reabsorption rate is now slowly deviated from this angulated curve, okay, and this slow deviation, you call it the splay. Now why this slow deviation is actually occurring is not all the 2 million nephrons of our kidney have the same tubular maximum reabsorption rate for glucose. Okay, we say that the tubular maximum reabsorption rate for glucose is 375 milligram per minute, but it is not found to be present in all the nephron, due to which some of the nephron would start to excrete the glucose in the lower glucose concentration in plasma only, and the curve will be slightly deviated, okay. And also they have found that the reabsorption process of the glucose in the renal tubule is not completely irreversible, okay. That may be the reason due to which the urine the glucose has started to appear. But we have to remember this very important mechanism, that is, if all the nephrons of our kidney had the tubular maximum reabsorption rate for glucose 375 milligram per minute, then we would have this reabsorption curve linear relation, okay, linearly sharp and angulated. You can see this kind of graph you could see. So linear relation you can see in the reabsorption rate below 375 milligram per minute. But actually we are seeing the deviation, because not all the nephrons, they have 375 mg per minute as the transport maximum. So yes, this is splay, and why it is occurring we have to understand. And more than that, we have to know how much is the actual renal threshold for glucose, okay. So whenever the renal glucose for the threshold in the venous blood, whenever the plasma glucose in the venous blood exceeds more than 100 milligram per deciliter, then the urine will start to appear, glucose will start to appear in the urine, and this point is the renal threshold for the glucose, which you can see in the conditions like diabetes mellitus, okay. So today we have discussed about how does the reabsorption occurs in the kidney. So there are the transcellular and the paracellular pathway. Then we also discussed about the reabsorption of the glucose with the help of transporter present in the apical side as well as the basal side. And importantly, we also came to know about the renal threshold for glucose, which is different in the actual condition and in the predicted or the calculated value, due to which while we are plotting the graph, here we can see slight deviation, which we call it the splay, okay. So this much for today, guys. If you like this video, please press this thumb icon, and then if you have any questions, do comment and subscribe, and also subscribe to our channel. Thank you.